So, dear colleagues, today we have a seminar, Impact of Asymmetry Measurements at SPD on Understanding Gluon Distributions, presented by Amaresh Datta. Is it correct pronunciation?
Close enough. Thank you.
Okay, please start.
Good morning, everybody, and welcome to the seminar. I will talk about not just the measurements, but the impact of the asymmetry measurements at SPD. So, to start, to give the context of the impact that SPD measurements will make, I have to start with a little bit of history. So, in the early days of probing proton as a composite particle, the tools that people had were the structure functions that you can describe the protons. So, in the large energy scale and in the leading order of coupling constant, you could write down the unpolarized and polarized structure functions of protons in this way. So, the unpolarized structure functions, oh, this is not very sensitive, as functions of Bjerken scaling variable x and energy scale, and then the longitudinally polarized structure function as a function of the same variables. And the main, mind you, these structure functions were essentially quark structure functions, to be more precise, essentially involving up, down, and strange quarks with vanishing contribution from strange quarks. And the main strategy on experimental side was to bombard the proton targets with beams of electrons or muons and look at the deep inelastic scattering of those leptons off of those protons. And you calculate the structure functions. Now, as you know that at large x, the structure functions are supposed to scale with the scaling variable, that is the Bjerken scaling. And it was found that at very small x, as you go smaller and smaller in x, this scaling property keeps breaking down. And that deviation from the scaling at small x essentially hints that there are contributions from gluons. So, it looks something like this. So, on the left hand side, you notice this is the unpolarized structure function, electromagnetic structure function of proton, essentially the world data, the collection of all different experiments. So, notice two things. First, the energy scale, the coverage in energy scale, multiple orders of magnitude, and the same goes for each of the different lines for corresponding to different scaling variables going up to different orders of magnitude. And notice that as you go smaller and smaller in x, you see the breaking down of the scaling, and that gives you information about gluon. But when it comes to the polarized structure function, the picture is not so nice. The first thing you notice is that you are very limited in energy scale, orders of magnitude smaller than the other picture, and also you don't go much farther in terms of the scaling variable, which is something like 0.003, corresponds to something like this. And notice where you had multiple data points to see even here the scaling violation, here you hardly have any data at all, so you can't even draw a straight line. So, it clearly shows that the deep inelastic scatterings were inadequate to give you information about gluons. So, we come to the next best thing that you can do. You can look at the scattering of hadrons with hadrons, polarized hadrons with hadrons, protons with protons, where you have the probability of different quarks and gluons interacting perturbatively, and then again forming with a non-perturbative probability forming some kind of final state hadrons. So, here you can probe directly different quarks or gluons or a number of combinations of all of them. So, that is the scenario essentially a few decades ago. So once it was found that the DIS experiments were somewhat limited in scope to access the gluon content, you start the other types of experiments. You have polarized proton-proton collisions, and that's exactly what was done at the RIC facility at Brookhaven National Lab, and STAR and Phoenix experiments. They started taking data in 2002, so just over 2 decades now they have been doing exactly that same thing. They are looking at Parton structure, spin structure with proton-proton collisions. And here at NICA, at Spin Physics Experiment, the SPD, we plan to continue that exact tradition and produce results that are complementary to the past experiments, and also other future experiments that are proposed and coming up soon in a few years, in the next decade. Before I move on to the details of SPD measurements, here is a quick side note. The electron ion collider, which is a proposed experiment at Brookhaven National Lab in place of RIC, so it's coming up now, they are reviving the deep inelastic scattering with new advancement in technology to push the boundaries of both luminosity and energy, so that now they claim that they can access large enough x and q square range to be able to look at the structure function and even access gluons, which was not possible a few decades ago. So here is a quick look at their pseudo data. So what you notice quickly is that the extension of energy range, and if you remember in our spin structure function world data, we stopped somewhere like 0.003, which is somewhere here. And in this case, EIC will have multiple data points there, as well as it will go much farther in and much smaller in X. So they will be able to see scaling violations, they will be able to access gluon content. So this is a fantastic example of how much technology and experiments have come over last 2-3 decades. The same technique is not possible before, and it's possible now. All right, so coming back to SPD, our polarized proton-proton experiments. So at SPD, there are many different programs, measurements planned at different stages. At an early stage when we will have less luminosity, less energy, and then at the final stage when we have our detector completed and we reach our peak luminosity and energy. And the main focus at that time will be to access the gluon distributions. So we want to make measurements that are sensitive to the gluons. To that end, we will have 3 major probes or particles that we will measure in our detector. One is the first one is the charmonia. So for example, GSI. So it has to be, as I mentioned, our main focus is to probe gluons. So we want interaction subprocesses that are sensitive to gluon components. So at SPD energy, the leading mechanism of charmonia production will be gluon-gluon fusion. They'll produce a CC bar pair and they will hadronize to form either GSI or psi prime or chi sub C1, chi sub C2. And we will measure them primarily via di-mu1 decays, which we will detect in our SPD detector or range system. And then comes another diagram, which is the prompt photon production. Come on. All right, so again here you have an interaction which is sensitive to the gluon components. You have a QG scattering producing another quark and a photon directly. So this, now notice, you will notice something that the production of the final state gamma or photon does not involve another hadronization process like here or like here. So this is a very clean channel for interpretation, but it has its problem, which I will come back to. And then of course the third channel of particular interest is the production of heavy or charmed mesons, which are produced in a mechanism something like this. So, the dominating process is gluon-gluon fusion, producing again C bar, but this time these are they do not hadronize together to form charmonia, but they produce separate mesons. That is why they are open charm mesons. So, this is our highest statistics channel because it has a high cross section, but it also has a very high background, and I will come back to this analysis in detail towards the later part of my talk. So, notice that my talk does not just mention the measurements. I talk about the impact of the measurements, and why is that important? Because this is a new experiment. So, for a new experiment, and especially for an expensive new experiment, it is crucial to do something new and not just test the results of other experiments that have been done or simply reduce the uncertainty with more data. So, you need to justify what you are doing in terms of manpower, time, effort and money. So, it is crucial that we establish that the measurements at SPD produce results that probe structure functions, spin structure functions of partons in an area which has not been done by other experiments. So, this is precisely what we mean to do. And at the very first point of that is that the SPD kinematics, the energy at what we will operate, 27 GeV center of mass energy, already ensures that it will probe the parton spin distributions in an area, in a kinematic regime that's has not been accessed by other experiments. For example, both the previous proton-proton experiments and other future spin experiments will operate at much higher energy, and therefore they will probe much smaller x. So, you already know that we will produce results that are complementary to other experiments. And then comes the question of quantitative measure, how much we will be contributing to the knowledge of PDF. So, to get a quantitative measure, we look at the Monte Carlo simulations, and we produce something like what you have just seen for EIC. We produce some sort of pseudo data through simulations and study its impact on the current picture of the spin PDFs, for example, helicity, sieverts, etc. So, in particular, I will talk about two different channels out of these three. I will talk about double helicity asymmetry measurement of prompt photons and its impact on helicity function, and then transverse single spin asymmetry measurement of D-mesons and its impact on possible impact on gluon sieverts TMD. Okay, so I'll start with direct photon. As I have already shown, this is a diagram, this is a schematic of the diagram, which is the dominant prompt photon production mechanism at SPD energies. But this is not a full picture. So, of course, this is sensitive to the gluon, which is very nice, and it does not involve a fragmentation in producing the final state particle, which is very nice because we have a very clean channel and its interpretation is easier. But there are some caveats. For example, this is not the only diagram where you can have a prompt photon. You could have here, this is a quark gluon scattering into a quark and a gluon, and that quark fragmenting or producing as a radiation another photon. That will also behave exactly like a prompt photon coming from this vertex. Or you could have a QQ bar annihilating, producing another quark anti-quark pair, and one of those quarks radiating a photon. That will also mimic the behavior of a direct photon measurement, prompt photon measurement. But not all of those photons sensitive to the gluon PDF. So, there are some dilutions, but those are small contributions, and as I mentioned, this is still the dominating diagram. It will produce it will contribute the majority of the prompt photons produced at SPD. So, it's still very sensitive to the gluon, which is a nice thing. And then experimental challenges are the background. So, your signal is a very high energetic photon, which we will detect in our calorimeter. But there are other things that could mimic the signal, for example, most of the backgrounds come from decays of neutral light mesons like pi zeros and etas, which will decay into 2 photons. So typically that's not a problem, because if you detect both photons, you can calculate the invariant mass, and you know that this comes from a pi zero or an eta, and you discard those photons. But if for some reason one of the pair is not detected, then of course the other one mimics as a direct photon to your experimental counts. And also if they are energetic enough so that your calorimeter resolution cannot separate the 2 photons, both photons will hit the same cluster and it will behave like a very high energetic single photons. Again, that's a background. But fortunately, those can be calculated in Monte Carlo simulation, and you can estimate those backgrounds. So taking those into account, here are some numbers. So we have the next to leading order calculations of theoretical estimates of double helicity asymmetry of photons produced from NNPDF unpolarized functions, and for polarized PDF, the DSSB 2014 sets. And then using Monte Carlo simulations at SPD, we produce how many such counts will be there in, let's say, 1 year of data recording, and also an estimation of the background coming from the decays of pi zeros and etas. And so that sort of gives you a systematic uncertainty of your counts. Now combining those uncertainties and the theoretical calculation, you see here a sort of pseudo data, just like I mentioned for the EIC. You have the ALL of photons as a function of transverse momentum and with their corresponding uncertainties. And now comes the question of how do we measure, how do we quantify the impact of this measurement on our current understanding of the helicity PDF. So to give that, I need to give some background of how those helicity PDFs are calculated. So I'll start from some primer of very briefly how those are calculated. So for example, you can extract PDF either unpolarized or polarized from something called a global analysis, where you gather data from different experiments, deep inelastic scattering, semi-inclusive deep inelastic scattering, proton-proton scattering, and then you either have cross sections or asymmetries depending on whether you want unpolarized or polarized PDFs, and you perform a global analysis. So very briefly, here are the steps. You write your Parton distribution functions as functions of x and q square, you parameterize them, and you convert them to something called the Mellin moment. This is very similar to Fourier transform. You transform them in a different space. The reason is, I did not show. So the cross section of a process like this is essentially convolution of certain non-perturbative and perturbative parts. So you have non-perturbative PDF, Parton distribution function here, here, perturbative cross section that you can calculate, and again another non-perturbative part of fragmentation functions. And all these parts are convoluted and integrated at the end, which is a very computation intensive process. But if you go to the Mellin moment space, those convolutions become products, which is much easier to calculate. So you have PDFs, you go to a Mellin moment space and you calculate the perturbative cross sections of the scattering separately. You combine them with the information about fragmentation functions and you calculate the asymmetries. And you convert back from Mellin moment to our regular x and q square variables. Now, but that's not the end of the story, because the PDFs can be, those PDFs can be at any energy scale. You can have start with any energy scale, but all these different experimental data, each one of them is probably done at a different energy. So all those results are from completely different energy scales. So you have an evolution equation so that you can convert your theoretical calculation to the appropriate energy scale of the experiments. And then you can calculate then you can compare apples to apples essentially. So now you have theoretical estimates or calculations of the asymmetry, and you have measurement from different data sets. So you can calculate the chi-square distribution between the calculated and the measurements, and you minimize them with Lagrange multipliers. You have some sort of chi-square distribution, find the local minima, and for that minima you extract all the parameters that you started with for your PDF sets. Now you have a proper Parton distribution function, either polarized or unpolarized. So that's how we extract them. So here is an example of the DSSB group, which is Daniel De Florian, Sasso, Stratman, Vogelsang, 4 people. So I just show this as an example to show that as you include more and more data from different experiments, your understanding changes. Your PDF becomes different. They have a completely new form as they include more and more rig data. So this is an example. All right. So this is how you extract, let's say, the PDFs. Somewhat recently, okay, so that's already 4 years ago. So this same group started using a slightly different technique, a more statistical approach to the whole process, which has actually been used for a long time by this NNPDF collaboration, and you probably all know about them. They have a huge collection of new and updated PDF sets of all different patterns. So in this way, remember you had the global data from different sets of experiments. So those are just one data point from each of the experiments. You have, let's say, pion uncertainty or kaon pion asymmetry, kaon asymmetry, jet asymmetry, whatever it is, from one experiment, one data set. But what happens if you could have an ensemble of that data? Let's say, imagine if you had 100 compass experiments, 100 Hermes experiments, 100 star, 100 Phoenix. So each of those experiments will measure slightly different result with their uncertainties. And given that most things in nature are Gaussian, probably they will follow a Gaussian distribution. So let's say pi 0 asymmetry will have a Gaussian distribution with certain standard deviation. So the idea for this type of approach is that because we don't have those 100 different experiments of the 100 different copies of the same experiments to perform those measurements, what they do is the next best thing. They take each data point, take its uncertainty, and assume that's the standard deviation. So they create a Gaussian distribution of the measurement of each experiment. And then you can randomize. You simply take a random combination of each of those measurements, something like a parallel universe. In a parallel world, you will have those sets of measurements. And in a different world, you will have a different sets of measurements. Now, for let's say you take 100 such possible random combinations following that distributions. And then for each of those sets, you go through the whole hog. You perform this computation intensive process for each of those randomized sets. So for each case, you extract a set of PDF. So what do you have now? Now we have, now you have a bunch of replica PDF sets for however many times you randomize. It can be 100 sets or 1,000 sets. And this is precisely what you see here. Each of these lines are one replica PDF extracted from the randomized distribution of experimental results. So not one set of results, a distribution of experimental results. And then of course it's a beautifully statistical approach where the average gives you the central value and the standard deviation simply gives you the natural uncertainty of the PDF. For example, you can see the blue line, the solid line, and the 1 sigma uncertainty range with the dashed lines. But remember, as I said, this was a computation intensive process. So why would you make life difficult by doing the same thing 100 times or 1,000 times? And here comes the reason. Why do you do that? Here's the beauty of this approach. So once you have extracted that set using a certain global combination of data from different experiments, now if you have a new measurement, you don't need to go through the entire process again. What you do is you reweight each of the PDF sets by with some weight as a function of the chi-square of that PDF's replicas ALL and the measured asymmetry, and you refit all of those replicas. So this Bayesian reweighting is essentially equivalent to a complete refit without actually doing the whole process. So here is an example of how this works. So one of the digest asymmetries from star experiments, which was not included in the original extraction of those helicity PDF, can now be estimated how much it affects whether the central value or the uncertainty. And here you see the effect. So these are the sets of replicas. This is the original version, the blue line, and the center, as you can see, this is really not good. The central value changes somewhat, and also the uncertainty bars. So I give all this extra information to show how we quantify the impact of our SPD measurement. So this is the mechanism, and using that mechanism, now we can try to use our pseudo data. Let's say this is our new measurement. So how much does it impact our understanding of helicity PDF? So now we can use that extra measurement and go through the entire process. So we use our estimated ALL, projected uncertainties, which corresponds to 1 year of recorded data, let's say integrated luminosity of 1 inverse femtobarn, and we take DSSV helicity PDFs, which has 1,000 replicas. You weight them, you re-weight them with some sort of weight function, which is a function of chi-square, where chi-square is essentially the difference between the pseudo data measure ALL and the ALL calculated using any given replica. And once you have done that, the reweighted distribution looks like this. So this is the central value, this is the delta, the first moment of the helicity PDF. You see that it doesn't, the central value doesn't really change significantly, but then if you look at the ratio, it gives you some beautiful information. For example, it shows that as I said a couple of slides back, that we know SPD will make contributions in large Bjorken X region, whereas star, Phoenix, or EIC will make measurements at much smaller X, where SPD is unique is we make contributions somewhere above X equals 0.1. So as you can see, somewhere around this region, this is where we make the largest impact. So we reduce the uncertainty by, come on, by almost a factor of 2, somewhere between X equals 0.3 and 0.5. So this is one way to quantify how much impact a new measurement from SPD will make. All right, so this was the impact on helicity PDF using prompt photon. Now we'll change gear and move on to a different channel and a different PDF. So next up is we want to look at the charmed mesons and how it can help our understanding of gluon PDF. So I have shown this already. So this is the leading mechanism. So at 27 GeV, this type of processes where a gluon fusion producing 2 charmed mesons will contribute about 70% of the all charmed meson production. There are other diagrams possible, of course, which is you can have a QQ bar annihilating, producing a CC bar, but that's, as I mentioned, it's a smaller contribution. So that will be the rest 30%. So, it is of course, this being the dominant diagram, production of these charmed mesons are heavily sensitive to the gluon distributions. So, if we measure transverse single spin asymmetry S sub n, those are some of the excellent quantities that can access the gluon Siffer's function. So, again we perform Monte Carlo simulations using Pythia event generator and SPD root, which is a GO4 based description of the detector and a CERN root based reconstruction software combined. And we estimate the uncertainties of such possible pseudo data or measurement of the neutral as well as positive D-mesons. So, we for the simulation we include the vortex detector, which will be used for reconstructing the secondary vortex of the D-meson decays, straw tracker for momentum, for tracking and momentum determination of the charged tracks. And the vortex detector used for this simulation was MAPS based, 4 layers with barrel and end cap parts. The event beam profile was used as a Gaussian with 30 centimeter width. We also use the time of flight and aerogel in the end caps for a sort of realistic particle identification that mimics what we will have in our actual experiments. We have 2 different sets of data produced to study signal. So, we have open charm subprocesses and then minimum bias to study the all possible random combination that will produce a background for our measurements. As I mentioned earlier, that this is our highest statistics channel, but it will also have orders of magnitude large background. And we try to measure, our goal is to measure the D-mesons, both neutral and charged, via their hadronic decays into pions and kaons. The secondary vortex reconstruction is done with a Kalman filter based package called K-particle, and we require high quality tracks with enough heats in the vortex detector to be able to point back to the secondary vortex. And for the background, we combine all possible combinations of pions and kaons that can mimic being a D-meson. Now, D-meson mass being 1.86 GeV, we look at mass range sort of on both sides of that. It's a narrower range. I'm not showing the entire mass range. All right. So, here now, because there will be enormous amount of background coming from the minimum bias, simply because of random combinations of pions and kaons, we need to put some selection criteria to be able to beat down that, to reduce the background and keep most of our signal. So, one such variable is the decay length of the D-meson decays. And if you calculate something like the figure of merit, which is the signal divided by square root of signal plus background, you get an idea of exactly what's the most efficient cut to separate signal and background. So, around 200 micron, if you select events beyond or above 200 microns decay length, you keep most of the signal, which is the red line, and you cut down most of the background, as you can see clearly. But that technique does not always work, because for example, collinearity angle, which is the angle between the D-meson momentum vector and the vector from primary vertex to secondary vertex, essentially they should be the same vector. So, the angle should ideally be 0, but you want them to be a very small angle essentially. So, although your figure of merit might suggest you put the cut somewhere much higher angle, that's not really physical. So, you put a cut on small angle so that you retain most of the signal and you cut down bulk of the background, of course. So, I will not go into details of each of the variables that have been used, but here is a list of variables. So, you can see cuts on a bunch of different chi-square and distances, distance of common approach between the daughters, between the daughter tracks to primary vertex, to the secondary vertex, etc. And then with those cards, so to see the effect of those selection criteria, here are some of the plots. So in our Monte Carlo study of D plus measurements, we produce 20 million open charm events and 4 times as much minimum bias events. And once we reconstruct, we end up with the diagram on the left. So here you have the reconstructed D plus, and then with just 4 times as much minimum bias events, you already see a quite high background, which is essentially flat. So after reconstruction, you end up with 215,000 D plus and 3.6 million random background. But once we apply our selection criteria, all these conditions, you cut down the background severely. As you can see, from 3.6 million, you end up with just 2 random background events here. Here. And you also cut down on the signal, but you do retain enough of the signal events to be able to do your analysis. So that's our goal. But remember, this was simply a very artificially generated ratio of signal and background events. In real data, we'll have multiple orders of magnitude more background. So we do need this severe amount of background reduction. To be able to estimate properly how much background we will actually have in our real data, here are some of the relevant numbers. So keep this in mind that we expect from our design report that we should have about 360 million neutral pions, neutral D0s decaying into this channel, and 520 million of positive D-mesons in 1 year of data. Here their corresponding branching ratios, and in the open charm events generated by Pythia, about half of the events have D0s, and about 1/5 of the events, have D plus. So we take all this into account when we scale our Monte Carlo sample to 1 year of projected data. For example, in our Monte Carlo analysis, we generated 20 million events, about 1/5 of them will have a D plus, and this fraction will actually decay into our channel of interest. So we practically, in our Monte Carlo simulation, produce these many events that we are interested in. But we know from our CDR that that number should be 520 million. So then our scaling factor is a simple ratio of the two numbers. The same goes for minimum bias, and here notice that, as I mentioned, I simply generated a small number of minimum bias events. But in real data, for 1 year of recorded data, this will be 33 trillion events, which I of course cannot simulate that many events. So we have a huge scaling factor, and that's why I mentioned we'll have multiple orders of magnitude higher background than our signal. But luckily, we found that we can beat down that signal by an enormous amount too. So that's always good for us. So at the end of the day, we have the final scale factors for signal and background to scale our Monte Carlo to a projected count for 1 year of data. Now, once you have the counts, how do you calculate the uncertainties? So that's not quite trivial. So I'll give a little bit of detail. So typically for an analysis like this, so it's done in a very similar way for all our similar and sister experiments, something like all experiments that does this type of measurements, STAR, Phoenix, or COMPASS. What you do is you have an invariant mass spectra, and then where your signal is, you also have some background always. So you can measure your asymmetry and your uncertainty where you have both the signal and the background. So that's your raw asymmetry. And then you cannot separate the signal, but you can separate the background. So far from the signal, you can choose the background dominated area, and you can also calculate asymmetry of only background and its uncertainties. So for each of those blue and red regions, you can calculate the asymmetry as a function of your azimuthal angle, and then you do some error propagation, and you end up with its statistical uncertainty of this quantity. All right? But this looks quite messy. It's a function of polarization P, azimuthal angle, relative luminosity R, and n phi's are the counts of your whatever your probe is, for our case D-mesons, in each of those phi slices. But you can make some simplifications. For example, the relative luminosity should be very close to 1. Unless your uncertainty is very high, you can say the counts for two different polarization orientations are very similar, and with those assumptions, you end up with a much simpler format of the statistical uncertainty. So this is 1 inverse square root of twice n, where n is your count in each of your bins, phi bins. So as I mentioned, you measure this asymmetry and uncertainty separately for the blue zone and the red zone. Blue zone is all counts including signal and background, and red zone is only background. So once you have that, once you have the uncertainties and asymmetries, how do you extract this, the asymmetry and uncertainty for only signal? You statistically subtract the background asymmetry, and you statistically add the background uncertainty in quadrature, and you scale them with the amount of background in your sample. So this is the final number that you want to plot, that you want to publish. So this is your signal, whatever it is, for our case D-meson. So that's your signal of D-meson and asymmetry and its statistical uncertainty. So from our counts, remember we did a hard work of calculating the Monte Carlo simulation, and we had counts of D-mesons, our signal and background, and then you can distribute them in certain phi bins, and for each of the phi bins you calculate the uncertainty, and then you can combine for all such phi slices, azimuthal angle slices, you combine them properly statistically, and then you can have your final statistical uncertainty. Now, what do you want to do with that uncertainty? So here are some of the theoretical estimates of the transverse single spin asymmetry. So these are calculations from our colleagues from Samara University, Vladimir Saliv, Anton Karpyshkov. And what you notice here is that, first of all, this is not an extracted, no, I'll come back to that. So these are uncertainties, so these are asymmetries for D-mesons, for SPD kinematic conditions, for two different parameterizations of the gluon-Sivers function, the SIDIS one parameter set and the D'Alessio group's parameter set. What you will notice here is the y-axis. So this axis is 10 times higher than this. So what this tells you is that depending on model or parameter set, you can predict asymmetry 10 times higher in one model than in the other model. And we don't know what's true because we do not have enough experimental data to distinguish between the two. And that's precisely where SPD makes an impact. Remember, we started with impact of measurements, not just the measurements. So this is where a new experimental result at SPD can make an impact. We hope to be able to distinguish between such large differences of model dependence. So where does our measurement make an impact? So here it is. So I mentioned all those scale factors. So from my simulation, you can project how much signal and background you will have in 1 year of recorded data. And that looks something like this. So as you can see, this is log scale. So you have orders of magnitude higher background. So we need to bit down that background to be able to see anything of the signal. And that's why we had all those selection criteria, a bunch of cuts. So with those selection criteria, you bit down both signal and background, but now you end up with more signal than background. And now you can fit the entire distribution, and this looks something like, remember the other analysis, something like this. You have a high signal peak and some small background under the peak. This is where we are at, like this. So now you have signal and background, and we go through the entire process that I mentioned of calculating uncertainties for signal plus background and background, then subtracting and correcting to get the signal. So you do that, and you end up with these uncertainties. Okay? So this is for neutral D-meson. However, these asymmetries, these are simply two different lines picked up from these plots. So these are essentially the sum, the black lines for each of these plots shown here. And now when I put them on the same plot, you see how much different the two different models predict. Okay? And sorry, where am I? Here. So for neutral D-meson, and here exactly how we hope to make an impact. So given the uncertainties that we hope to achieve, we should be able to distinguish whether this model is favored or this model is favored, right? So this is for neutral D-meson, and we can do the same exercise for positive D-meson. You see the similar plots, you fit the signal plus background, you go through the whole hog, you have less counts here, so you have a larger statistical uncertainties. This is simply, we do not have enough surviving data at this point, so this is just an infinite, so forget that point. So the idea is still, even with positive D-mesons, we should be able to distinguish between this model and that model. All right, I have come to the end of my talk. So what have we shown? The SPD measurements will probe the different PDFs, TMDs at essentially large Bjorken X, which is complementary to present and future experiments, so that we don't walk the same path as the other experiments have already done. We have shown that the helicity PDF extracted from SPD can make contributions above x equals 0.1, and in particular, to be more quantitative, direct photon asymmetries, direct photon double helicity asymmetries will be able to reduce uncertainties by almost a factor of 2 between x 0.3 to 0.5. And remember, this is only direct photon, but we have 3 main channels of probes. We also have J size or Charmonia and D-meson. So we have not looked into ALL measurements of those channels. In fact, Igor Denishenko and Anton Karpiskov have already looked at the impact of J-psi ALL by extending exactly similar techniques, and we see again we make large impacts in large X region. And we are yet to do that for D-mesons, which is nice. So that's for helicity PDFs, and for TMDs, remember this is a relatively new field. There is no globally extracted gluon-Sieverts function yet. So very recently, by recently I mean 2020, the Jefferson Lab groups called JAM collaboration, JAM, they have extracted quark PDFs, and that's the very first extractions of, not PDF, quark Sieverts function. And there is no gluon-Sieverts function, simply because we do not have enough experimental data to do that. So first of all, measurements at SPD will produce, supply those new data points so that in future some people can extract those gluon-Sievers function. And for the time being, when we do not have an actual gluon-Sievers function, what we can do is we can distinguish between prevalent competitive models of the gluon-Sievers function. We have seen that different parameter sets can predict as much as 10 times more. One model can predict 10 times more asymmetry than the other model. And we can distinguish that. When we do the measurements, hopefully we will be able to favor one and disfavor the one. And so that's precisely a huge impact that that SPD single spin asymmetry measurements can make. So in future, we look forward to more careful simulations and extending our techniques to estimate the impact of gluon helicity for also the D-meson double helicity asymmetries. That's all from me. Thank you. Sorry for the very long talk.
Okay, thank you, Amaresh. Promising simulation, very interesting. Please, questions. Yeah, please.
So, thank you for this nice talk. So you mentioned about this gluon-Sievers functions.
Mm-hmm.
So how do you define that theoretically? Is it possible to say, for example, from some Wigner distribution, or how is it connected?
So it depends on, the applicability depends on whether you have enough. So it's not properly factorizable, right? So depending on your kinematic regime, it's difficult to interpret. I don't think I can comment in exact detail of how they are parametrized and calculated. These asymmetries are calculated from our Samara colleagues. Off the top of my head, I cannot comment exactly how they are parametrized. By any chance, Igor, do you remember? Sort of applicability of gluon-Sievers function for our kinematic range?
Probably too much. Not too much, but there are, I remember, processes that are TMD factorizable, which are not. So in particular, GPSI production is not exactly TMD factorizable. But what people say, so we think that factorization, probably this violation of factorization are small. And for example, ETA-C production should be is TMD factorizable, but it's very challenging. We don't know whether we can have a chance to see its signal. But anyway, that's there are TMD factorizable processes also for the associated production. I don't remember reason, but GPSI photon is treated as TMD factorizable, double GPSI production, and some other. But what just people usually say that we believe that this factorization break-in is not too large.
Thank you. Any more questions, please? Maybe from Zoom? No. Okay, thanks again, Amaresh.
Thank you.